All right, so I just rewrote all the findings we had about the Laplace transform. And when I wrote this down, I decided to write this first and then put that afterwards. And now I have to show you how this Laplace transform is helpful in solving differential equations. Now, before I do that, I want to show you just one more calculation. What would I get if I applied this formula to f double prime of t? Well, f double prime of t is the derivative of f prime t, so all you have to do is now replace f of t on the right side as f prime. Okay? So you have s times L of f prime of t minus f prime of 0. But then this one is here, right? So I can again write s times Laplace transform of f prime of, no, f of t minus f of 0 minus f prime of 0. And if you multiply the s inside, you get s squared Laplace transform of f of t, and then s times minus s times f of 0 minus f prime of 0. And actually you can do this many times. You can do this to Laplace transform of f triple prime of t. And you can kind of guess what's going to happen, right? Instead of s squared, what would you get?
S cubed.
S cubed, right? And instead of that, you're going to get s squared of f of 0 minus s of f prime of 0 minus f double prime of 0. Okay. And so on and so on. Okay? You're going to get that. And I need to still write it in a different form. Often when you write down the Laplace transform of a function, unknown function, you use capital of the same letter and you use s. Because if you take the Laplace transform of a function of t, it gives you back a function of s, right? So that's the symbol that people use. And because this formula looks horrible, people usually write it in the following format. Let me write in red. So we have this. Okay. And then this one, using that terminology, we can say Laplace transform of f prime of t is s times, instead of this, I use capital F of s minus f of 0. And Laplace transform of f double prime of t equals to, what is it? F of s squared f of s minus s f0 minus f prime of 0. Okay. So that's what I have. And actually after this the list grows. You have a few more. You actually have a table of Laplace transforms. But just because I want to show you a demonstration quickly, instead of showing you more fancier ones, I'll just put two more. So cosine of t gives you 1 over 1 plus s squared. And sine of t gives you s over 1 plus s squared. I hope I'm right. Let's just hope that we're right, because we don't have time. Okay. All right. So now I want to show you the following question. What is y double prime plus y equals to t minus 1 with y of 0 equals to 0 and y prime of 0 equals to 1. Now, this can be solved using Laplace transforms. How do you do it? Well, you take Laplace transforms both sides. And because Laplace transforms are linear, meaning that you can distribute to each terms, that's because it's an integral operator. We just went over that, right? So L applied to y double prime can be solved using this, right? So what does that give us? It becomes, can you tell me? L applied to y double prime is s squared, and then? You don't use f, you use capital Y, okay? Minus s times y of 0 minus y prime of 0, okay? And then plus L applied to y, what's that? Huh?
Shouldn't that just be 1 over s squared?
No. That would be L applied to t. If I know that y of t is just t, then that would be true, but we don't know what y of t is, right? So L applied to y is just still some unknown one, and we decide to call it y of s, right? Remember? And our goal is to find out what y of s is, right? Okay, what's L applied to t? That's 1 over s squared, right? L applied to 1? 1 over s. Okay, now you plug in 0 for y0, 1 for y prime of 0. So you have s squared y of s minus 1 plus y of s equal to 1 over s squared minus 1 over s. Let's move the constant term to the other side, and you get s squared y of s, y of s, that's comma, so let's factor that. And on the right side, this is s squared, and you get 1 minus s, and this is plus 1. Minus 1 goes to the other side, becomes plus 1. So what's that? 1 minus s plus s squared over s squared. And then finally, we can divide this out, and we get capital Y of s equals to 1 minus s plus s squared over s squared 1 plus s squared. Okay, at this point you might be amazed, like, what? We have the solution? Do you have the solution? No, we know that the solution of the original equation is not like this, right? It first has to be a function of t, and we also know that the complementary solution is sine and cosine. The particular solution should be at plus bt, right? At plus b. That's not in no way the same as this one, right? And if you think about it, this is the Laplace transform of the yt. We didn't get yt. We have to go back somehow. Okay? Now, so there are some important things that we see at this point. We see that if you take the Laplace transform of a differential equation, you get an algebraic equation, which you can solve easily. There's no differential to worry about. It's just algebraic thing. Another thing is that it's easier to solve if you have the initial condition. If the initial condition is not given, then you have to use C1 and C2 for the initial values. That makes the final result very messy. Okay? So usually you want to use Laplace transform method to solve only if you are given the initial conditions. Okay. All right, and then now how do you go back? That becomes actually the big part of Laplace transform solution. You go back by writing this as a over s plus b over s squared plus cs plus d over s squared plus 1. You have to find A, B, C, D. Where have you done this before? When you did integration, you had to do partial fraction expansion, right? That's what you have to do. Okay. How do you do it? Well, you multiply this to the other side. I'm going to do a more systematic approach, but let's try to do this quickly. Okay. So if you multiply this to the other side, you get A times S times 1 plus S squared plus 1. B times S squared plus 1 plus CS plus D, and then S squared. Okay, that's what you get if you multiply S squared times 1 plus S squared. Okay. Now I just want to plug in S equal to 0. Why? Because if you do that, then you get 1 on the left side, but all of these are 0, and you get just B. But B is 1. Oh, that's nice. And then I want to plug in S equal to I. Why I? Because I squared is -1, so these vanish. Right? No, these two vanish. And you're left with this. What about this one? 1 minus S plus S squared. So it's 1 minus I plus I squared, which is -1. That's CI plus D. And S squared, I squared is -1. Okay, so they cancel, so you get -I equals to -CI plus minus D. So the real part is 0. This is 0 plus -1, so D should be 0. And C should be 1. Okay. And then to get A, you do something called matching the highest order. So if you multiply A S S squared, that's AS cubed. That's CS cubed. And that's the only time you get CS cubed on the right side, right? S cubed. So there's A plus CS cubed on the right side. Whereas on the left side, do you see S cubed? You don't, right? So A plus C must be 0. So A must be -1, right? So now you're ready to plug in -1 here. B is 1. C is 1. And D is gone. And now once you have that, you can guess what the original function is. So try to figure out what this is. What gives you -1 over S? 1 over S gives you 1, so it must be -1, right? What gives you 1 over S squared?
T.
T. What gives you 1 S over S squared plus 1? Sine. That's it. That's the solution to the original equation. So, of course, this trying to do partial fraction, that's a lot of work. There are some other reasons why you want to do it this way, but we'll go on, and then I'll explain more as we go. Yeah.
Will we get a permission to do Laplace transforms?
We will.